Hello everybody. So this is the last lecture of our course of practical implementation of network coding for the summer semester 2020. Uh, I will talk a little bit about error correction with network coding. In the previous lectures, we always look at network coding as a code to correct for erasures. So the decoders would always get correct packets, error-free packets, or no packets at all. Those were the only two possibilities. So we didn't took into consideration what would happen if some packet have errors. So that was not discussed. In this case, I will tell you a couple of techniques that we have worked on to exploit the properties of network coding in order to correct errors. So when we transmit a packet over the network, usually at the physical layer and at the MAC layer, there are added some error correcting codes, some forward error correcting codes, and these codes try to correct some errors that could happen in the air when you transmit the packet. So traditionally or usually the packets have this structure. This is the structure of an IEEE 802.11 packet, and it basically has some header to address the source and destination, and it has the actual data. So basically this is from all the layers above. All the data of those layers is added here, and then it has some bytes reserved for the FCS. This is a 32-bit cyclic redundancy check. So this is a code that allows us to check if the packet has errors or not. So basically what happens, or what tends to happen, is that these packets are transmitted over the air. In the air, they might have some errors might occur, and when they arrive at the destination, at these lower layers, the forward error correcting codes solve these errors or correct these errors, and then the packet is given to the upper layers error free, or this there are errors that could not be corrected, in which case this FCS, this CRC, also called the cyclic redundancy check, would fail the check, and then the packet would be discarded. So basically, this is a hash that is computed with the bits, or with all the bits of the packet. So basically, if there is one erroneous bit that could not be corrected, then this CRC would fail. This layer would know that there was an error that could not be corrected, and then this packet would be dropped. So it's interesting to know that even if there is one erroneous bit, only one bit, after the corrections of the forward error correcting code, even if one bit it's not correct in the packet, the whole packet will be discarded. So if you see how many octets are as part of the data of this packet, discarding all of that information just for one erroneous bit doesn't seem too efficient. So let's see how network coding can make it a little bit more efficient. So this technique is called PRAC, which stands for Packetized Rateless Algebraic Consistency. Here you can see the original paper. You can look at it. And it works in the following way. Let's assume that we have a generation size of 2. We have 2 packets in our generation, packet 1 and packet 2. And they look like this. In the following slide, I will describe what you are seeing in the slide, and at the bottom you will see a legend of the colors. So these slides will be available in Opal. You will have access to the slides, and you can read them later. So here's a legend. So these are the original packets, packet 1 and packet 2. How does network coding work? Uh, Network coding would choose some coding coefficients, C1, C2, and C3. It will multiply the packets by these coding coefficients, and it would generate 3 coded packets. They are in this darker shade of blue. So now we have M1, M2, and M3. These coded packets will be transmitted, and in the channel or which is transmitted, there might occur some errors. These errors might not be corrected at the decoder if there was some forward error correcting techniques at the physical layer. These errors might not be corrected, and then these are the packets that arrive at the destination. We color coded the errors in purple. These are errors that, for the example, we know where they are. But if you think about a decoder, the decoder does not know where the errors are. Because of the CRC fail, here you can see, because of the CRC fails, the decoder knows that these packets have errors, but the decoder doesn't know where exactly these errors are. So this is what the decoder receives. He receives M1, M2, and M3 stars. Star because it went through the channel, and there are some errors. When it computes the CRC, it realizes that these two packets have errors. In traditional networks, in IEEE or 802.11 networks, this packet would be discarded. As we discussed, one bit would discard the whole packet. But we can make use of the algebraic consistency rule, which is something that PRAC makes use of, to decode the information that is encoded in these three packets. So intuitively, we know that these coded packets were generated by the linear combination of other packets. So we can exploit that to correct these errors. So I will go through the process of how this is done. The first step in PRAC for the algebraic consistency rule is to select a subset of the received packets equal to G, to the generation, and taking as many correct packets as possible. In this case, the subset will be of size 2 because our generation is 2, and we will choose the one packet that we know is correct because the CRC was okay, and then we will choose randomly one of these two incorrect packets. In this case, let's choose M1 star. So this is the first step. We choose these two packets. The next step is to assume that these packets are correct. Let's imagine that there were no problems in the transmissions, that these packets were correct, and we will decode them, right? In traditional network coding, decoding technique. How is the decoding done? So if you know what are the coding coefficients used to generate this packet, you can write them here. And you have to invert this matrix in order to decode, right? If you remember from your linear algebra lectures, an easy technique to invert a matrix is to put the matrix you want to invert and put the identity matrix on the side and perform operations to obtain the identity matrix here, and whatever remains on this side of this matrix, you perform the same operations, right? Whatever remains here would be the inverse matrix. If we do this here, we would obtain this. So this is basically our inverted matrix. So then to decode, we have to multiply our coded packets by the inverse matrix, and then we would find the original packet. If we perform this, we would obtain these packets, and this is what I call guessed original packets because they are decoded, like network coding would decode them, but we know they are errors, right? Because we are analyzing this from an example perspective, we have some form of God view And we know that if we have an error here, when you do the multiplication, that error would appear here. So in the same way, when you produce this packet by multiplying by these coefficients, the error would appear here. So, however, the decoder doesn't know where exactly are the errors. He just knows that this will have errors somewhere. The next step to identify where are the errors is to use the coding coefficients of the packet that we did not use in these first steps and generate what would be called M2 star star. So if you remember, we receive M1 star, M2 star, and M3 star. Those were the received packets. We used M1 star and M3 star to decode the original or the guessed P1 and P2. That's why they are called P1 star and P2 star. But there was a third packet that we did not use so far, which was M2 star. So basically now what we are doing is that with those packets that we decoded, we will encode again, like if we were a network coding encoder, we will encode again M2 star. In this case, we will call it M star star because this is produced with different packets that were decoded by this PRAC decoder. And then we just have to compare this newly decoded packet with the M2 star that we obtain from the transmission, from the actual transmission. And we then evaluate symbol to symbol, symbol wise. We evaluate where they are equal and where they are different. In those places where they are equal, we know that there are no errors in those locations. In those places where they differ, we know that there are errors. So because of this, we see that in the original packets, not the original packets, but the packets we received over the air have errors in these two symbols. So in this example, the way how I structure the errors, right, made it clear here that these regions will, or these symbols will be different. However, if there are errors in the same locations, depending on the errors due to the linear combination, it's possible that with this technique, those errors will not be located, will not be identified. And this is due to the probability that when you multiply, do these linear operations with those erroneous symbols, they will turn out to be the same symbol here than here. And this would be a false positive. You can find the details on the paper that was cited there, and it depends. It's a function of the finite field used. So the larger the finite field, the lower the probability of false positive. So if you're interested, look into that. But in this scenario, there is no problem, there is no error in the detection, but then that's why we can actually decode with practice. So, okay, so to continue now, the decoder knows that the errors are in this region. So in these packets, M1 star and M2 star, the decoder knows that there are errors because the CRC failed, and now he has a region where he knows where the errors are, and that region is these four symbols, because that's what the algebraic consistency rule told it. And now the correction happens. So the first step is to choose one of these packets that was received with errors. It could choose any of these two randomly. So let's say he chooses M1, and then it will do a brute force of bits. So the first thing that he will do is to change the bits in the positions where he knows their errors, or where he thinks they're errors, which would be this position and this position, and then compute again the CRC. So in this case, he would start, for instance, placing all bits to 0, 0, 0. And then he will compute the CRC again. The CRC will fail. We know with our gut view perspective that it failed because this is wrong. Then he will change again to 0, 1. Now we know that these two are wrong. Therefore, the CRC will fail. And then he will try the next combination, which would be 1, 0. And in this case, the CRC is correct. Now this packet has been corrected. Now we have M3 star, which is correct, and now we have M1 star, which was corrected. Because our generation was of size 2, now we have two coded packets that are correct and linearly independent, then we can decode. If we perform the decoding with the inverse coding coefficient, then we obtain the two original packets. So as you can see, we corrected errors using network coding and exploiting this algebraic consistency rule. We see that to do this, we need at least G plus 1 packet. So our generation was 2. We needed 3 packets in total, counting partial packets. Partial packets are those with errors, and valid packets, and which are correct packets. We needed 3 in total to decode. So we did a first decoding with 2 packets, and then we did the algebraic consistency check with a third packet with G plus 1. So we did at the chair, we did some performance evaluation. I will talk a little bit about that. So we did some measurements to evaluate how well could PRAC perform, and we had this setup. So we had 2 offices, one in front of the other, and we had 3 devices that were connected to a Wi-Fi access point, and they were listening. We set their network interfaces in promiscuous mode, which means they would listen to every packet that was on the air, and we had a controller which was automating the measurement campaign, and it was also transmitting wireless packet to a unicast destination that was very close to it. So the idea was to transmit packets from this node to this node. Since they were very close, they would basically be almost no lost packets here, so there would basically be no retransmissions. If you know, Wi-Fi has a built-in retransmission to correct these erasures, right? We didn't know we want to reduce the number of retransmissions. So we just place it very close, and then these 3 nodes would listen to all the packets that were being sent to him, logging them. So the idea is to see how many partial packets we got and how many packets we were not lost and where were the errors. So that was our intention. We wanted to see if this transmission would have been done from this controller to this node, what would be the performance if we try to decode with PRAC, or if we just use traditional network coding. So this is how our setup looked like. So over here in this office, we have the listening nodes. Here we have the access point. Here we had the controller and the unicast destination. So he was sending packets to him. And those nodes over here that you can see on the picture on the right were listening to with this wireless interface, we're listening to all the packets that were arriving. So what was happening? So we logged all the received packets, and among those packets, if you see the frame, the errors can occur at any point of this frame. You could have errors at the CRC code. You could have errors, bit errors that could not be corrected right at the header, or you can have bit errors at the at, at the data part of the packet, right? If you have errors in the CRC or in the header, then we would not really know if those are really the packets we are interested in, because we cannot see what are the MAC addresses involved. We cannot see any of this. So then those are packets. So let's say this bar represents all the transmitted packets. So those packets that have errors in the headers were could be listened, but because they have these errors in the headers, we were not sure if they were the packets transmitted by our transmitter. So then we discarded them. So among all the transmitted packets, we had some packets that were lost, that were erased, they never arrived. We had some packets that arrived with errors in the headers. Those packets were discarded. We had some packets that arrived with errors in the data part of the packet. Those were our partial packets, and then we had packets that arrived without any error at all, which is this green bar. This is how many packets we received. So we use different modulations for the transmissions. So you could choose the modulation you want. So in 11G, which works in the 2.4 gigahertz frequency band, we transmitted at different rates: 54 megabits, 36 megabits, and so on. Each dot represents 10,000 packets transmitted. So this is how many discarded packets in the number of received packets we have. So if we transmit with little transmit power, so on the x-axis you see the transmit power, on the y-axis you see how many packets are discarded, and each dot it's 10,000 packets. So if we transmit with little power, we see that we discard a lot of packets. So there are a lot of packets that are so broken that we cannot do anything with them. If we increase the power a little bit, then the number of discarded packets is reduced. The bar represents the means, and each dot 10,000 packets. For IEEE 802.11n, which works on the 5 gigahertz frequency band, we also use different modulations and transmission rates, and you see how they behave. So this is basically how many packets were discarded. We wanted to know how many packets we could use, how many packets were so broken that we could not use at all, or so broken, or at least not necessarily so broken, but broken in the header in there, that would not give us too much information about where were they routed to, or who wanted those packets, who requested those packets, and so on. And we see that if we want to have a useful amount of packets, then we needed to increase a little bit the transmit power. These were the initial measurements to know what parameters should we set for the transmissions. We were also interested in evaluating why these packets were discarded. There are many reasons to discard these packets, and here you can see for different transmit powers, you can see the percentage of discard packets, and then you can see color-coded the reason. So there are many reasons, like the UDP data length was invalid. Why is this invalid? Why is this number not correct? Because the error occurred in the header. So all of this information is basically in the header. If the errors are in the header, then depends on what part of the header the error is, then this data would be incorrect. So the UDP data field was missing, or the IP of the destination was incorrect, or some MCS was missing in the case of 11N, and so on. So this is all the reasons why we were discarding packets. Most of the time, when we discarded a packet, it's because the IP layer was completely missing. So to do the analysis of the received packet, we use Wireshark. So we were logging in as I told you, with the receivers, we were logging all the received packets, and then we were analyzing them. And this is how the bits error probability, or yeah, the individual bit error probability looked like. So we were transmitting packets that were 14,000 bits long, and we logged a lot of these packets, many of these packets, and then we saw if a packet was valid and it had an error in some bits, in which of those bits this error occurred more likely. So then we can see this plot. So for different data rates, we see what is the probability of each individual bit to be erroneous. We were expecting a straight bar for different reasons, but we thought that the errors were independent of the position of the bit in the packet. It's also because we were using some interleaving, or the MAC layer uses some interleaving and so on. So we were expecting a straight line, and it's interesting that that was not the case. So what we saw is that the last bits of the packet are most likely to be erroneous than the initial bits of a packet. That is very interesting. This is for 11G, and the values for 11N look like this. We submitted a paper to Globecom. It hasn't been accepted yet, but there we also talk about why there is this periodic shape here. You can uh, have that paper if you ask me once it's published. And then we wanted to evaluate, as I told you, right, what is the potential performance that PRAC can have. So one of the limitations of PRAC, as you saw, is that it involves for the correction a brute force. It brute forces bit flips in order to correct the CRC. If you think about it, if you have a long packet and the CRC fails, right, you do not need PRAC if you will brute force bit. So you can take your packet, your erroneous packet, and you can flip each individual bit one by one and compute the CRC over and over and over again. But if you have thousands and thousands of bits in your packet, right, this process will be very computationally intensive. So PRAC, what PRAC does is it exploits the algebraic consistency of the packets. Algebraic consistency is because everything was made with linear combination of something. So the packets, there must be some consistency between them. And those places that are not consistent, as we saw, allows us to reduce the search space. So you can think about brute forcing as a way of correcting the packets that we could use with or without PRAC. But since the packets are so long, we would need a lot of computing power that is limited. So then we need a technique to reduce the search space. And in this case, algebraic consistency rule allows us to do that. When we reduce the search space, then we can correct the packets. So we did this potential performance, or we evaluated what would be the potential performance based on the received packet. So for example, if we look on the right side, we have a partial ratio of 36%. It means that of all received packets, 36% were partial, which means that they had some form of error, right? So we have here different, in color, we have different computing powers for PRAC. So in this case, we said that blue is no partial packet recovery. It means that there is no PRAC or no other technique. Yellow means that we have a PRAC algorithm that can correct up to 4 errors, because more errors would require more computational power, because it would require a lot more bit flips. So we say, okay, it's limited to 4, and then we would have certain improvement. Then if we increase the computational capacity of PRAC to 50, then we would have a higher improvement. In the case where we have a PRAC that can use all the computing power of the infinite computing power, right? Then we would have in this case performance increase of 27%. It means that we could make use of all these packets that arrive that were partial that we could not use without packet recovery. When we have a higher ratio, we have higher range gains. It means that if half of our packets are partial, it means that now with PRAC we can make use of some of them, and we have some gains. So PRAC, an infinite computational powerful PRAC, could bring these gains in these measurements for these particular setups. And then we also consider as a baseline a perfect partial packet recovery. This would be a packet recovery technique that can correct every erroneous packet received, every partial packet received. So as I told you, this would be, for instance, brute forcing all single bits of the packet and computing the CRC without using PRAC, just getting every erroneous packet, flipping bits, and computing the CRC over and over again. Why do we have this gap here between that perfect partial packet recovery and an infinitely powerful PRAC? Isn't they the same? Well, not, because PRAC requires G plus 1 packet. So if we draw this line, if we see this plot, this is the number of decoded packets on the y-axis. On the x-axis, you have how many received useful packets you have. And the color coding means the ratio between correct and partial, right? So over here on the top right of the plot, we see that out of 10,000 packets, 10,000 there were no partial packets, so all the received packets were useful. Remember, each dot represents 10,000 packets. It means that here all 10,000 packets were received. So basically, out of 10,000 received packets, we have 10,000 decoded packets. So this is the best we can do. PRAC, because it works on generations, right? And it needs one more packet per generation, that would bring down the potential recovery of PRAC. So basically, if we are in this region, the best we can do with PRAC, or at any region, the best we can do with PRAC is decoding in this straight line. And that's why there was this gap between a perfect partial packet recovery and PRAC, because of this limitation that we need one more packet per generation. So this is as part of our measurement campaign, we wanted to see how many packets we could decode. So as predicted, we could decode as many packets we can decode as many packets that are on top of this line. However, there were many packets, especially when we were receiving very little useful packets. There were a lot of the time we were decoding a lot less packet than we expected. So as I said, we expect to decode, if we use PRAC, we expect to decode all the packets, or at least as many packets as how to say. So we expect all of these points to be on this straight line or above, because if we have an infinitely powerful PRAC, PRAC would decode this many packets based on this straight line as depending on the received useful packet. So PRAC would decode all these dots would be on this straight line. If we receive more packets that are useful, that those imposed by the limitation of PRAC, then we can decode a lot more packets. That's why these packets would be above this line than those using PRAC, because we do not have to get G+1 packet to decode G. Over here, we can decode G out of G. Down here, we can decode G out of G+1. But we noticed that even though we were considering in our simulation infinitely powerful PRAC, there were some packets that could not be decoded, that were these dots were not pushed to this line. They were still below. So then we were curious into why was this happening. So there are two possibilities of why PRAC cannot decode. One of the possibilities is imposed by the hardware, which is the computational power that we can have, right? We can limit the number of errors that PRAC can try to decode. So as I told you before, we can say, okay, PRAC can decode up to 4 errors or up to 7 errors, or up to infinite errors. That would be infinitely powerful by PRAC. But it also happens that PRAC gets what I discussed at the early, that are the false positive, which is that based on the finite field that we are using for our simulations, we use binary 8. The way how the errors were located in our generations would produce a false positive. It means that the algebraic consistency rule would not detect the errors. Using bigger field size would reduce this probability. So we saw that if we have a limited, computationally limited PRAC, it means a PRAC that can correct up to 250 errors, right? The orange dot represents the probability of PRAC failing due to too many errors. So this is the partial packets, relative or normalized to the total number of packets received. So a 1 here would mean that all the received packets were partial. In this case, there are too many errors, and it cannot decode. And if it sees that there are too many errors, it doesn't try to compute to decode, so it doesn't detect the false positive. On the other hand, if we assume that we have a PRAC algorithm that can correct every error of the packet, this were the length of our packet, right? Then there will never be too many errors. That's why the orange dots are here. But when the packets are more and more broken, this is, the x-axis represents how broken the packets are. With 1 means that all bits are erroneous. So in this case, there are many scenarios where PRAC would fail due to false positive. So we thought if we want to fix this, one of the ways to do it, one of the ways to fix it is by increasing the field size used. However, another way to address this problem is to reduce the size of the packet. So if we have smaller packets, right, then if we have a false positive and we cannot correct it because of PRAC, then it's not too many bits that we are discarding. And then we produce these plots. So this is similar to the first plot I showed you, but we have 2 parameters now. P, which represents the packet length, and T, which represents how many errors PRAC can correct. So an error means erroneous symbol. Since we are using a finite field of 2 to the 8, each symbol has 8 bits. So on the left, we have a very limited, computationally limited PRAC that works on very long packets. And on the right, we have a PRAC that is not limited in computing power. It can use as much practically infinite computation power to decode. And in this case, we have also a long packet. So this is again the decoded packets as a function of how many receive usable packets we have. There are not so many decoded packets on this line because PRAC fails a lot of time due to computation power. It cannot decode more. If we increase the computational power of PRAC, we push more of these dots towards the line that I described, the G over G plus 1 line that I described. By shortening the length of the packet, we also have an impact on how many packets we can decode. In this case, by reducing P from 1400 to 250, by reducing the length of the packet, we can correct errors and decode a lot more packets. If we also increase the computational capacity of PRAC now to 250, right, then we can decode a lot more packets than in this case. And in the case where we shorten the packets a lot more, let's say P equal 50, so the packets have 50 bytes each, and we have either correct up to 4 errors or correct up to 50 errors, we see that we perform a lot better. This is very interesting because this how many corrections we can make is something that in this case we simulated based on the gathered results from our measurement campaign. But in a real application, right, the more errors you want PRAC to solve, the more computing power you have to allocate for it to solve it. So what we see is that we can increase the performance of our communication with the same data traces, right? All of these dots represent the same data traces. But if you consider shorted packets, you do not have to invest too much compute power to use PRAC and correct the erroneous packet, those partial packets. So why is this beneficial? What would be the point of using PRAC instead of requesting another packet, right? So one of the reasons might be latency. So if you consider future communication networks or for example IoT networks or places where there are massive amount of users connected, right? If you want to decode with our current techniques, right, with our current Mac techniques, you would need to get G, where G is the generation size, you would need to get G correct packets. If you do not get G correct packets, what IEEE 802.11 networks do is that they retransmit the packets until you get enough. When you get these G packets, then you can decode. So if you did not receive enough, and you are alone in the room or your device is alone in the room, then it's not a problem to request one more packet. Hey, retransmit that packet to me again, and I can decode. But assume that now you're not alone in the room. Now there are 1,000 devices in the room, and everybody wants to access the medium. So if everybody wants to access the medium, it means that retransmitting this packet to you would mean that you will have to wait until, if it's a fair medium access control mechanism, you will have to wait your share of the medium. So all the other nodes will try to transmit something, and eventually, when there is space for your transmission, you would get the packet. So for all packets to decode, you would need to wait until you get G correct packets. However, if you want to trade off some computational power, if you want to invest some computing power, you can use techniques like PRAC to decode the correct packets, the generation, based on these partial packets, which means that sometimes depends on how many errors you have or depends on how busy the medium is. Sometimes it might be faster to use computational power and correct the packets than to wait for retransmissions. So that's the benefit of using PRAC, right? Basically, we do not want to discard a full packet or a whole packet based on a few bit errors in that packet. Another technique to finalize, another technique that we have, it's called DAPRAC, which is data aware prac. You can find it in this paper. And the way how it works is a bit similar. So I will explain to you, instead of writing zeros and ones, right? Let's assume that each of these block is a symbol in the finite field. So zeros and one would be for a binary field, but this is not limited to any, this is not limited to binary field size. So this could be symbols in any field size. So let's assume we have packet 1 and packet 2. These are our original data. In DAPRAC, what we do is that we append a CRC code to the original data packets. So basically, this is done at the encoder. So this is the encoding process. And the encoder will compute a hash, a CRC code, on the date based on the data of the packets, and it will append it to this packet. That would be seen as part of the data now for the network encoder. So now the network encoder would again choose some coefficients, some coding vectors, and it will produce some coded packets. As you see here, the coded packets are one symbol longer than the original data packets because we have the CRC appended. In this case, the CRC has the same length as one symbol, but the CRC can be longer or shorter, so the CRC can have different lengths. In this case, it happens to have the same length as our original data. Then we transmit this over the channel, and again, because of errors, some bits are flipped, or some symbols, not so many bits in a symbol could be flipped, but these symbols arrive with errors because the forward error correcting codes could not solve these errors. So how would DAPRAC do the decoding now? It does it in a different way. So first we do something called predecoding. So we take all possible combinations of the 3 received packets and we decode with those packets. So in this case, let me explain. In this case, we will use M1 star and M2 star, which we know have errors because the outer CRC told us this packet have errors, but still we will use these 2 packets to decode with network coding these 2 packets, which are called P superscript 1, 2, 1. So this is the first pre-decoding. Then we take M1 star and M3 star and we decode, and it looks like this. And then we take M2 star and M3 star and we decode, and it looks like this. Because we are seeing this from a God view perspective, we know where are the errors. If you try to decode like this, you know that the errors will appear in those positions, right? But the decoder knows that this is bad. This was not correctly decoded. Now not based on the outer CRC, but based on the CRC that we added to the data. Because if we compute the CRC with these values, because there are errors here, it will not match. So we will know that there is a problem there. So again, these packets were decoded with M1 star, with M2 star. These ones decoded using M1 star and M3 star, and these were decoded using M2 star with M3 star. So now, again, PRAC, it's all about reducing the search space of your brute force technique. In this case, the search space is reduced by checking where these symbols agree. So in this case, this symbol is equal to this symbol, and this symbol is equal to this symbol. And similarly, those 2 symbols are equal to all these symbols. Here, those symbols will differ because the decoding, because it was not decoded with algebraically consistent packets, there will be errors here. And this part of the packet will be correct. So, or will be the same. So then we know now where are the errors. But because we have data already decoded, so this is like all decoded data. To do the brute forcing of the different symbols, it's a different process. So what we do is that we choose a set of pre-decoded packets, any of those two. Let's see in this case those decoded with M2 star and M3 star. And we will try all permutation of these symbols in the known error locations until the data CRC is correct. So from this packet, we will put this symbol here, and we will put this symbol here. If we do that, and then we compute ourselves the CRC, we will see that the CRC here is correct, and the CRC here is not correct. So we know now that this packet was correctly decoded, but we'll still need to find how to decode this one. The next step then would be to move this symbol here, for instance, to try that. And then we see, in this case, we compute the CRC and this matches. So in this case, now we just have to discard this inner CRC that we added, and we have our data decoded. So this was basically some techniques to do error correction with PRAC or with network coding. PRAC, if you see PRAC and DAPRAC, there is a difference in the way how computational power is used. So PRAC uses computation power to brute force bit flips and compute CRCs. DAPRAC does not brute force bit flips. It employs its computing power in performing a lot of decoding processes. So you saw that we had to decode 3 times, and but then the way how it searches for errors is different, because then what it does is that it uses permutation of these symbols and arranges these symbols in different locations. So instead of flipping bits one by one, it's not so difficult to correct, because you only have to move these symbols from one point to another and compute the CRC. So PRAC does a lot of bit flips and a lot of bit flips and CRC calculations. DAPRAC does a lot of decoding and then CRC calculations. When is one better than the other depends on the number of errors you have, on your generation size, but there is a trade-off on which one is computationally more efficient. For information about that, you can check out the paper that was mentioned there at PRAC. So thank you very much. This was the lecture. I hope you enjoyed. Bye-bye.